Okay, so we're going to begin our discussion on the differential amplifier here. Um, Essentially, the differential amplifier, as the name would imply, is it amplifies a difference in voltages. For instance, ideally, we are going to have the following situation. Ideally, we'll have some output voltage equal to some voltage gain times voltage 1 minus a voltage 2. Now, before we get into too many things here, well, and actually, we'll go VOL here. A VOL is referred to as the open loop gain. And remember, our ultimate goal here is to be able to design an operational amplifier here. And we remember that these open loop gains tend to be pretty high. And that actually, if you go back to the actual kind of dependent source model for an op amp, as opposed to just assuming infinite input impedance, we do have that the output voltage is the gain times V1 minus V2. Now, we are going to, so I, okay, let me get there. So if this is working exactly the way we want, clearly, if V1 equals V2, then V out should be equal to 0. And that's just obvious from the equation there. So we're going to define a couple other voltages here. So we're going to define something called the differential mode input voltage. And the differential input mode voltage is VD, and that's simply just V1 minus V2. And then we're also going to define something that's called the common mode input voltage. And these are all going to be important for us to do DC analysis of this circuit and then also small signal analysis for us. Common mode input voltage. And we're going to define this to be VCM is equal to V1 plus V2 over 2. Now, we will see why we call that common mode in a second here when we get into the DC analysis, because that's the first one we're going to analyze, is the common mode one. Okay, so let's look at the circuit here that we have here. So I'm going to draw a circuit for basic differential op amp here. So whoops. And I could have paused the video maybe to draw this, but you know, that's okay. So this is basically our basic differential amplifier here, and we've got VB1 and a VB2 here coming in, VC1 and VC2, and then we've got Q1 here, and we'll label some other things as we go here. Now I just want to emphasize this IQ here. I'll just put it here. This IQ is just my biasing current set up by current mirror. And notice how we don't have any kind of voltage division with the resistors on the base like we normally do. If you're thinking back to like electronics, like your first course on electronics. And the reason being for that is because we have both a positive and negative voltage, so we can bias these transistors in the forward active region. And because of that, we don't need any coupling capacitors and other things of that nature, which is nice. Okay, so we're of course going to make some assumptions here. We're going to assume Q1 and Q2 matched. And of course that's an assumption we've been making for all of these IC designs here, where these transistors are all matched. So that makes things and for simplicity here, well, I guess we don't have to do it for simplicity. We'll just say that the VBEs are the same, which we're going to take unless otherwise specified as 0.7. Now what we're first going to do is we're going to first look at this in common mode voltage. So if you want to think about this common mode voltage, this would be V1 here. You could think of this as V1 and this is V2. But common mode voltage, what we really are doing here, and let me just kind of erase some of these things. I'm going to be going back to this diagram and changing it. What we really end up happening here is we're connecting the bases together of these two transistors, and then what we're doing is we're applying the common mode voltage to both of them, which the common mode voltage is up here, which we can kind of then see why do we actually use this idea of V1 plus V2 over 2, is that the idea is we're basically averaging what VBE1 and VBE2 is. But now the DC analysis becomes pretty straightforward here, because since these base voltages are the same, this base voltage here is the same as this base voltage. Clearly the emitter voltages are the same. So what do we have here? Q1 and Q2 have same VBE. So IB1 equals IB2. But if IB1 equals IB2, then we get IC1 equals IC2, and IE1 is equal to IE2. Then making the assumption here that IC1 is approximately IE1, we get then that, just looking at this diagram here, looking at these currents coming into the node, this current leaving, we have that IQ is equal to I'll say IE, and assuming IC1 is approximately IC2, I get IC1 is equal to IQ over 2. But then what do we get here for looking for this VC1 and this VC2? These output voltages, because those are going to be my outputs. Then I get here that VC1, just doing a voltage drop here, V plus minus the voltage across this resistor. So this would be V plus minus IQ over 2, and that's what VC1 would be equal to, and then that is also equal to VC2. Alright, so that's all we're going to do in this first video here. And again, the key thing here is what we've just analyzed for this differential thing. This is in common mode input voltage. And you might say, well, wait a minute, you said V out would be 0. Well, what we're getting here, if you think of V out, could be the difference of VC1 and VC2. Then if they're the same, it would be 0. But the common mode input voltage, we get then that we get VC1 is V plus minus, oops, I forgot one major thing here, times the resistor. Alright, so that's where we'll end this video, as I said. And then we will pick up in the next video looking at the differential mode voltage.